I'm now going to talk about aligning coding sequences. This is where we just finished up. These are the unaligned sequences. In order to make a phylogenetic tree, just as it was important that we only put homologous sequences on the tree, the process of making a tree means that the sites have to be compared, the columns have to be homologous sites. And the process of alignment is one in which gaps are introduced so that in any column we make the best guess about what sites are homologous, and those gaps that are introduced represent historical insertions or deletions. So that's the starting point, and we'll pull down this, use MUSCLE as the alignment program. This is DNA, so the natural thing to do is to choose align DNA. But that's a bad idea. When it aligns DNA, it will put gaps in places that maximize the alignment score. And MUSCLE doesn't know anything about what this DNA is for. It doesn't know anything about codons. It doesn't know anything about anything else. All it knows about is improving the score. And it will introduce gaps that fall into the middle of codons. And if you've got a codon in there, if you translate that into a protein, then it doesn't know what the amino acid to put in. It's A gap G. No one doesn't know what to do with that. But the worst consequence is it doesn't just affect that particular amino acid. It frame shifts everything downstream so that any proteins that you want to look at from this are going to be completely screwed up. So instead of choosing align DNA, choose align codons. Make this a firm rule. If you are working with coding sequences, always align by codons, because that introduces gaps between the codons, not within them, and it always introduces gaps in multiples of 3 to keep the reading frame intact. So when you choose that, it opens up the analysis options. These are the default settings, and you can just go right ahead and click OK. And that's what the progress window looks like. MUSCLE, depending upon how big it is, MUSCLE can take a little while to do this. You just watch it till the progress bar reaches the end, or your coffee cup is empty, or whatever. And eventually, you have an alignment. Now, what I've shown, what it will show you is the translated protein sequences. And the important thing to notice through here is that they're all real amino acids. If you have frame shifts in there, it'll show you stop codons eventually. It'll show you questions if it doesn't know what amino acid to use or what amino acid it is. So it has worked. It's done a real codon alignment. And if you go back to the DNA sequence view, you'll see that over here, the number of gaps, why did it do that? The number of gaps that are introduced is always a multiple of 3. If you're very good, you can count those quickly. The alignment is done, and now what you want to do is you want to save the session. That saves the alignment in Mega's own alignment format. So you can come back and you can get to it and do anything else you want to with it. Always save things as soon as you can. Having saved that as an ebg.mos file, it will allow you to, I assigned ebgc aligned as its name so that I'll know that this wasn't the original where I saved the sequences. These have actually been aligned. And the last thing I'm going to do is export alignment and save it in the Mega format. And when it does that, it saves it in a format that Mega can now read to do what you really wanted to do with in the end, which is to make a phylogenetic tree. And that's it.